Thanks for coming. Very accepting here. Online.
Thank you. Okay, thank you for the invitation, and I'm very happy to come here again. Also, thank you everyone to attend this seminar. So today I'm going to talk about online DP coloring, and this is joint work with Professor Alexandr Kostochka at Illinois, and then Xuding Zhu and also Xuer Li. Xuer Li is a Xuding Zhu student. Okay, so we know many parameters in coloring. So we know the least chromatic number also, but maybe also some of you know the paint number. Also some of you, I think many of you maybe heard about the DP-chromatic number. So actually today I'm going to introduce online DP-chromatic number. So in general, the paint number is generalization or least coloring, paint online coloring. Also DP coloring is also generalization or least coloring. But the relationship between this paint number and DP chromatic number, the relationship is not very tight. We don't have a very clear relationship. But actually, the relationship is not good. The reason is there's some graph which the DP chromatic number is much bigger than paint number. But for some time, you are not sure if there's if there's a graph with this property. But in this paper, we we find a graph such that paint number is greater than DP chromatic number. So actually, it's final. So in general, we don't have a very tight relationship. So we want to find some. Okay, we want to find some common generalization of these two parameters. So we define the online version of a DP coloring. So and the good thing is it turned out this online version of a DP coloring is the generalization of these two parameters. So first, I'm going to explain what is the DP coloring also. And then I'm going to explain about the online coloring, and then I'm going to introduce the online DP coloring. So first, the DP coloring. The DP coloring is was introduced by Duborak and Postel to study the least coloring. Actually, there's some long-time conjecture that the conjecture is the planar graph without cycle C4 through C8. The question was, is it 3 choosable? It was a long-time conjecture, and then they proved the conjecture by they proved this conjecture, and at that time they introduced DP coloring. Why they introduced DP coloring is usually when you study least coloring, we cannot use the let's say it's not good. I mean, so sometimes we identify two vertex, right? We identify X, Y, J, X and G. In the coloring, sometimes to reduce some, to make a reduction, we make identify. We identify two vertices. But DP color in list coloring is not allowed. If the lists are different, such operation is not good. But in DP coloring, sometimes we are able to identify two vertices. That's why they introduced this deep coloring to overcome such difficulty. So here, key point is we convert the list coloring in. Oh, I'm sorry, I didn't fix the typo. We convert the list coloring to find the largest, to find the independent set in a new graph. So here, key point is if the chromatic number is n minus k, then the Cartesian product of Gn and complete graph Kk, their alpha, the size of largest independent set is at least the size of original graph. So actually, the key relationship is we are using this relationship. So let's define the deep coloring more formally. Actually, given a graph, we define new graph H, such that here is the list. List size 2, 2, 2, 3, and then we blow up each vertex according to this list. So 2, 2, 2, 3 vertex, and then inside we make complete graph, and then between set we have some matching, and then we want to check the alpha of H is the same as the size of original graph G. So but here between two sets we have a matching, but we don't know what kind of a matching. We just know there's a matching. Okay. For example, sorry. Okay. I think this one. Sometimes matching is like this, but sometimes matching is like close. So we have to assume all kind of a matching. And then, so now, for technical reasons, we call the matching between two sets by this capital M. And then this is more formal statement of the definition. The first line is the new graph H is the vertex set is this is all point. Second line means each set is complete graph, and then third one is we have matching between two sets. Then we want to check alpha of H is equal to the size of G. So here, each set is complete graph. So when you find independent set, we can select at most one vertex. So because of that, alpha of H is at most this size. So if okay, how can I say? So here we select the vertex here, but so this is coloring, so we call it coloring. So we call ML coloring of G means independent set I, such that the size is original graph. So if we are able to select this independent set I, we call coloring. Actually, we select point vertex, but this is coloring, so we call coloring. So then the DP-chromatic number, definition of DP-chromatic number is like this. So here, if this set is very large, then we have more chance to satisfy this, right? So like least chromatic number, the DP-chromatic number is the least integer k to guarantee this. So okay. Now let me give you some small example. Okay, we have a C4. We have a C4. Then we just assume, okay, there's the list size is 2. Then we have we can think, okay, this is one kind of match. In this case, we can select the 4 point. I mean, we have an independent set of size 4. Then this is good. But if matching is like this, then we are able to select at most 3 points, right? So it means the size 2 is not enough. So we have it means that by definition, DP-chromatic number is greater than 2. But here we know its choice number is 2, right? So this is one example. The DP-chromatic coloring is different from list coloring. And what is the relationship between DP coloring and list coloring? So if matching is like this, I mean, if you have we have list 1, 2, 3, 4, we have list 2, 4, 5, 6. So we have a matching. We just connect with the same number. Then it becomes the list coloring. The reason is in DP coloring, here 2 and 2 are connected, right? So when you're looking for independent set, we cannot select both of them, right? We select at most 1, right? Also in the list coloring, we can color only. We can choose only one place, right? In the list coloring. So we have a match like this, then it becomes list coloring. So this is how the deep coloring is the generalization of list coloring. And okay, let me give you one more example. Maybe that is. If the list is like this, then we just connect the same number like this, right? So if we define matching this, then this kind of case implied the list coloring. So here, if this is the DP colorable, then it means it's L colorable. So in general, so this deep chromatic number is at least the choice number because it is generalization of list coloring. But the interesting situation is for even cycle case, this deep chromatic number is always 3. But the choice number is 2. So also we can find many examples such that the deep chromatic number is greater than choice number. But good thing is many property of list coloring also hold for DP coloring. This is good. So for example, for planar graph, the choice number is at most 5, but deep chromatic number is also at most 5. Also, the planar graph of course at least 5 is deep chromatic number is also at most 3. So in general, our research direction is like this. Okay, we have this inequality. So if you have a very nice upper bound of deep chromatic number, then automatically it gives upper bound of choice number. So in this direction, maybe first we want to find very nice upper bound of DP coloring, chromatic number. Also, sometimes, actually most of the time, we want to generalize some result in least coloring to DP coloring version. So in the coloring, the Brooks theorem say the chromatic number is M-most maximum degree if it is not complete graph or odd cycle. And we know this story also hold for least coloring. And then deep coloring also. This is true this is true for deep coloring. I think that basically the proof is based on some degenerate concept. Right? When you're looking for upper bound, actually we just count number of bad neighbor, number of neighbor, right? Also, we know the degree choosable concept. So if the least size is at least degree, then still it is L-colorable. And then the nice property is if G is not, if each block, so that's a very nice theorem. That is, graph G is not degree choosable if and only if each block is the complete graph or odd cycle. And so our question is, can you have a similar story in DP coloring? Actually, yes, by the Anton and Kostochka and Ron, and they proved this. This is same story hold for DP coloring. Also, this story also hold for multiple graph. So now I'm going to introduce the all-line coloring. So basically, there's two people, the lister and painter. The lister presents some part of vertex, and then painter color properly. So this vertex should be independent set, and the later lister present another set of vertex, and then paint color.
So I2 must be subset.
Yeah. Should be subset. So we have a game like this. So here the goal is the painter want to color every vertex, and the lister disturb that situation. So here we have a notation. F of V token. It means some vertex it present how many times it present. So the token means the number of times that vertex can be appeared. So here, if the number of token is huge, then the chance the vertex V can be colored is very high, right? And whenever list include this vertex, then by just technical computation, we just reduce the number of remaining tokens. And then here, the painter win this game if he color every vertex, and then otherwise lister win. So here key point is, so f of v is the number of chance to be marked by the lister, and then the paint number is the list number k, such that always painter has winning strategy. And also, it turned out also this is a generalization of list coloring. Also, there's some graph H such that this paint number is greater than choice number. So, for example, this theta graph. So, I'm going to explain this case. Okay, we have this graph. This theta graph means usually let's call here x. We may have this part, it could be long path, but its length should be even. This part, this middle part, the length should be even. This how many? It's okay, right? If this part is odd, then the odd cycle. So, and then we can check this kind of graph is too choosable. But before this talk, I tried to check this, but it's not very quick. I mean, it takes some time. The why this is too choosable, I think you can generalize this situation. Actually, it is 2 complete by the 2k to 3. Then you can check this 2 choosable, and then generalize this situation to here. But because this length is long, then I realized it is we have some more cases, but still true. So now, in the online coloring case, we have 2 token, 2 chance, but I'm going to show 2 chances is not enough. The reason is like this. First, list present only these 2 vertices. Then number of tokens reduced to 1. And then this is adjacent, so painter color only 1, right? Not both of them. So we have here's 2 choices. So let's assume, okay, painter color V1. Then later, then lister present now these 2. But the previous time, it has only 1 token. So if lister present these 2, paint has no choice. He must color this. Otherwise, later he cannot color V2. So now he color already V1, V2, and then later lister present this and this V3 and X like this. Then also painter must color V3. So now lister present these 3 vertices like this. Then again previous time vertex X has only 1 token. Then painter must color. Then the remaining token like this 1, 1, 2. So now painter present these 2, and then lister presents these 2. Then painter must color G. Then finally, lister present both of them. But no more token left. Then 1 color can be colored. There's 1 color, painter cannot color, right? So painter lose. So if lister present another way, in that case maybe painter have winning. There's some way painter can win, but here the lister is smart, right? So in this case, the lister win. So it means anyway, the two chance is not enough. So here the paint number for this case, actually the paint number is greater than 2. Then why this concept is a generalization of the least coloring. Here, like this. Okay, so in the formally, okay, just the V as a list like this, right? And then here if the lister present according to this rule, then it becomes just list coloring. So for example, we have a list like this. Then first round, lister present the vertex only which contain color 1, like this. And the second, lister present the vertex which contain color 2. And the third case, and the lister present vertices which contain color 3. So if lister present this way, then and if this is online colorable, then it means in the list coloring case, we are able to color everything, right? So that's why so here if G is online two colorable, it means G is L colorable for this list. This is why the online coloring is a generalization of a list coloring. So in general, so this paint number is a list choice number. Also, we can observe many property of list coloring can be extended to the online coloring version. So here one of the main question was how much this gap can be large. I mean, we know there's some graph. The paint number is greater than choice number, and the previous example was so can you guess previous example what is that? Only one. Okay. For some time, until that time, only bad example is the gap is only 1. So question is gap is always at most 1, or some big number, maybe 10, or really bad cases, gap could be arbitrarily large. So most people are not sure which is correct. So many people believe maybe this kind of thing, I mean, the gap can be small, but it turned out gap can be arbitrarily large. So this Polish people, they proved that the gap can be arbitrarily large. In this case, they compute the paint number of this complete bipartite more precisely. So now, I'm going to introduce the online DP coloring. So as I explained before, the main target online DP coloring is the generalization of this these two parameters. Here, we have DP coloring, but we play by online version case. For example, in DP coloring, we have a matching like this. So in online DP coloring also we have a matching. But in DP coloring, we give a matching everything at once. Right? But online version, we give a matching some part. We hide the other matching. We give some part of matching. So, okay, first round, list give only this part. Later, second round, list give only this. Third round, list give only this part. So we give just partial matching. And then painter want to select the independent set. And then it turned out this concept is generalization of the deep coloring and online coloring. So why? If at the first run, if I give you all matching, no hidden matching, then this is deep coloring. And if I give you matching, just one single matching each round, then we can understand, okay, this is same as online coloring.
I'm confused with GIP. So what's that notation?
This one?
Yeah.
Sometimes, the degree is 1 or 0. This vertex is degree 0. So only the degree 1 vertex present. Okay.
But when you present, you might have many.
Yeah. So
yes.
yeah, a little confusion.
Can you show us a definition of GI cover? That's yeah. Can you show the definition of GI cover?
GI cover is GI cover means this new graph H. Yeah. And in the new graph H, some part of H.
So you don't have connectedness.
Basically, we want the connected component. I should go back to. Okay. This is H new graph H, yeah. And the GI cover means I just present a part of this. Yeah. But always we present connected component, connected graph. So in this case, actually this, connected means we just forget inside this. We just consider it matching. For example, okay. Here, if matching is like this, then first line I can present inside this cycle. It means I present every vertex.
And you need to take a representative for each vertex in the component.
Yeah.
So you're sort of taking an induced subgraph, yeah, and saying what the matching is on the induced subgraph.
Yeah.
Okay.
But the matching means yeah. And the degree 1 means only this. We just consider only these two vertices. Actually, this degree 2, right?
I see. So the lister choose. So lister select the subset of vertex of G, which induces some components in the eventual cover. Right? Okay.
So in this case, actually, the original graph H, this we call this the H cover. So in this case, actually, this is connected component, right? In this case, this must present everything.
Oh wait, so to represent the subset of H, not G, right?
Yeah.
So initial graph has only 4 vertices, but lister present 8 vertices.
Yes, exactly. Yeah. Okay. Let me show it again. The list must present the connected component, connected graph. So in this case, list can present all or only this part, right? And the second round, we can present another C4. But in this case, this is connected graph, right? So list cannot split. When list present, it cannot split. So it seems like the online DP coloring is not very different from DP coloring. Because the list have some limitation, because list should present connected graph. I mean, the graph means that is everything.
So really, list has always to choose the whole connected components, and then as an induced subgraph, and then choose the sum of each of the. Okay.
Okay, so let's go back very quickly.
Like you cannot choose an empty match between.
Okay. Okay, we must. So relationship between the online DP coloring and the paint number, the online coloring is between two vertex. The matching is only one edge. The first round, he may present this one. Second round, he may present this. Actually, this is actually the typo. I mean, between two sets, the degree 1, but
What is G now? Just an edge?
G.
The graph G? I don't know.
Graph G is, we don't know, just this is U and V is the vertex of graph G.
Okay. But I thought this has to choose something from a whole component now, and not just from one edge. Or can you choose just one edge?
Lister, in this case, he can choose only one vertex here, because if he wants to present this component, the lister should present only this. Lister can present only this and this.
Okay. I don't understand.
Yeah, but it might have other vertices, and this may continue to. So this is only part of.
This is only part of the list. Okay.
Okay. Any other question?
The V value could be greater than 1 if you have, like, you choose U the second round, so the two value there is 1, we could have other.
It could have another label. So this notation is correct.
The value could be greater than 1.
The vertex may have many edges coming in this GI cover. We still have to choose the independent set.
So we're looking for the property of online deep coloring. And so far, good thing is, so many nice property of least coloring, deep coloring can be extended, this online version. But always we have this bad guy. And what is that? Actually, we are able to show just paint, just online coloring version. This is greater than DP. And then the online DP is greater or equal to paint number. So this example also show this one. But we don't know what is the gap. In this case, I think just n must 1 or n must decimal number. Because still, honestly, I'm not very sure how much different online deep coloring is from deep coloring. So my feeling, I think not so much different.
So is it whether DPP and just P? Is there a gap there, or is it not?
No.
Not now.
That's maybe no many.
Between the paintability number and online DP-chromatic number.
Yeah.
So for example, as I showed before, this is, but basically it is 2 log n plus n must. And then this is increasing ratio is this much. And the gap is very, very big.
Between P and DP.
Yeah.
That's P and DP. Now I want to DPP.
You know this, right?
Yeah, right. But can this is this a real gap? I want to know.
DPP is greater than equal to this.
Right. Yeah. Okay. I see. Okay. How does that?
The graph of that theorem look like?
Which
first one? Right. Yeah. The gap between that one. How does that look like? Is it complicated?
Example?
Yeah.
Okay, let me show you. We have here each set x and y. Here 2k minus 1 point. Here also 2k minus 1 point. And then here the matching. Let's call this h. And then we know, then the least size is this is k, the inside vertex, it is 2, everything is 2, but here k. So this is DP color, this graph, but not online color. This part, given this size, this is deep colorable, but not online color. And then we have many 2k minus 1 new point. And we connect many over here. Okay. Yeah, also, okay, here, let me see. Here we have a huge number, k, 2k minus, sorry. this one, k 2k minus 4 copies. We have this many copy of H. Then we have a new point, new vertex 2k minus 4 point, and we connect nicely. Then we are able to show still this. Okay, let me see. This new graph is DP k-colorable, but not. Let me like this. We can show because of this many vertex. In online coloring, we able to color this, and then the one bad example remain of this shape. And then this, and with this list, we know it's not online color. So construction is like this. Sorry, I skipped the detail. Okay. I think the answer for this question is very interesting. But I'm not sure. But I think gap can be, I think it's not arbitrarily large. And then for degenerate concept, so for DP-chromatic number is M mod D plus 1. Also, this is extended to online DP coloring version. And then the degree choosable, also we can extend. The degree choosable also we can extend in the online DP coloring version. And then what is next? The typical, the thing, this planar graph case. Also, we can extend the online DP-chromatic number of planar graph is M mod 5. And then, yeah, maybe that's all I would say. Thank you.
Thank you very much. If any questions? Okay.
So is it known whether the paintability number can be arbitrarily larger than the DP-chromatic number?
No.
That's not known.
If it's yes, then you already answer.
Then I wasn't sure if it was known to be false.
You already answered this.
Yeah. So it is known that the DP-chromatic number can be arbitrarily larger than the list chromatic number as well.
Yes.
But is it possible that these numbers are tied?
I mean, the gap between DP and choice number?
Yes. So that can be arbitrarily large.
Arbitrarily large.
Could those numbers be tied? The functions.
Tied meaning if one is bounded, the other is bounded.
Yeah.
Is that what you're asking?
Yeah.
If we have such a thing, then it is very interesting. Actually, I want to know such function. So for example, do we know some? You are asking this kind of thing, right? Yeah. Also. If ever, let's call the other function. If ever this function, if ever this function is this interesting. And by Xuding Zhu, this one is here's this function. think here it means the yes. In combinatorics we always use 2, right? Many times, but this case.
I mean, ln already.
But sometimes when I read the paper, number is a little different what I expect. Then I realize sometimes we use E, sometimes we use 2.
Right.
You're right. But including me, many Korean we mixed.
So this ln part cannot be an constant.
Huh?
Ln n cannot be replaced by a constant.
Can you improve this?
I mean, can you replace this ln n by a constant?
This one?
Ln n.
Replace log n with a constant.
Log n.
Can you reduce it? To,
Yeah.
to
This
constant?
one?
The log here, and then
Yeah, this one.
can
No.
you-
Yeah, is that
Is
no?
it tight?
No. The question is no. The answer
Answer
is
is no.
Okay.
Answer is no.
So it's known that it cannot be a constant.
Because complete bipartite graphs.
You mean this part?
Yeah. Okay.
Yeah.
Right.
It's complete bipartite graphs are two
Yeah.
colorable and least chromatic.
It cannot be constant.
It goes by this. Those. What was the function for the paintability of complete bipartite graph?
You already erased it.
That's
Wasn't it like end of the road or something?
You can say like this. Or if you use this one,
There's a lower bound, right?
right? Upper bound. This is upper bound.
But there's a lower bound for paintability number. For complete bipartite graphs or?
Lower bound.
Oh, there's a least chromatic number, right? Least chromatic number is arbitrary D.
Yeah.
Any other questions?
Just for the classical chromatic number, is it known what kind of function? Between like this chromatic number and chromatic number, is it known what the best?
No.
But
Complete bipartite graphs are.
Complete bipartite.
yeah.
They have arbitrary large least chromatic
I
number.
know that the gap is infinite, but how fast can it grow? The gap,
In terms of what?
in terms of the number of vertices that you got.
That I don't. Any other questions? Since he's gonna stay until the end of this week, so we can probably go and bother him. That's more work. Alright. Yeah, let's thank the speaker again.